The hardest part was over, but I still had to add a few controls. I decided to keep these simple, 3 buttons to navigate through all the settings, and a potentiometer dial to control the tempo. I'd be using a piece of copper strip board to solder on the buttons, and I also needed to add 1 resistor for each button. This circuit diagram is showing just one of the buttons. The symbol on the left, I02, represents pin 2 on the Arduino. I0 stands for input-output. When an Arduino pin is set to be an input within the software, it becomes able to detect if there is a positive voltage connected, known as high, or if the ground is connected, known as low. A floating pin, where neither high or low is connected, causes erratic behavior, so you always want the input connected to something. So one side of the switch is wired directly to the Arduino. The other side of the switch is connected to the ground. Therefore, when the button is pressed, the Arduino input becomes connected to the ground as well. This resistor is known as a pull-up resistor. With 5 volts connected to the other side of it, it ensures that apart from when the button is pressed, there is always some positive voltage running into the Arduino input. The reason the 5 volts can't run directly into the Arduino input is because when the button is pressed, without the resistor there reducing the current, the ground and 5 volts would be directly connected to each other, shorting the entire circuit. I could have wired this circuit the opposite way, using a pull-down resistor instead, which on a small simple circuit like this would work equally as well. Whichever way round you wire it, you just have to make sure your code knows whether high is on or high is off. In this circuit I chose to use a pull-up resistor because I think it's more commonly done this way. Here's an expanded circuit showing all 3 buttons. It works exactly the same as the more simplified version I just showed you. These dots are a junction where everything is connected. When there's no dots, such as these, it means there's no electrical connection between the crossing paths. I've used 22,000 ohm resistors, usually referred to as 22K. However, to be on the safe side, I recommend using somewhere between 4.7K and 10K for most 5 volt pull up and pull down applications. The PCB buttons I'm using have 4 legs, though really they only have 2 connections, as there's 2 pairs of electrically connected legs. If you're not sure which way around they go, it's a good idea to check their operation with a multimeter set to the continuity test mode. Learning how to find answers is often better than knowing the answers. So the closer together legs, here on the left and right, aren't connected until the button is pressed. And it makes no difference if you use the front pair, the rear pair, or in diagonals. And the pair of legs on the right and the pair of legs on the left are always electrically connected. Giving the copper rows a good clean on the strip board can make things easier, making sure the solder flows nicely. So now I'm plugging the button into the strip board, being careful to make sure the pairs of electrically connected legs are in the same copper row. The first track will be for ground, with a wire soldered to the right. Then there will be a wire attached to the output of each button. That will go to the Arduino inputs. A 5 volt wire will be soldered to the board. Then resistors will link the button outputs to the 5 volt track. And finally, the track that has the button output will need to be broken in 2 places, leaving 3 separate track sections. Resistors don't matter which way around they go, though I like mine to be neat and all facing the same direction. When soldering components with wire legs like resistors, it's convenient to hold them in place by bending them. However, this can cause issues blocking the hole next to it. In this case, I solder the legs going into the spacious power strip first, which holds the resistor in place. I then unbend the other leg next to the button output before soldering, as that might have blocked the hole that the wire needs to go into next. I really should have clamped the board down. I was being lazy. The wobbling isn't making my soldering any easier. I'm now using a strip board cutter to break the tracks. If you're confident in your planning, it's best to do this before soldering anywhere nearby. If it touches a bit of solder, it can tear your whole track up. Also, the copper particles can sometimes get caught in cracks and cause electrical problems later on. By the way, be careful never to breathe in the dust from these strip boards. Hearing myself take a deep breath just before I blow the dust away doesn't seem too sensible. Making sure the buttons are nice and flat before soldering them. I think it's best to start off soldering just one corner and then turn it over and check it's still flat. You might need to push them down some more and possibly remelt the solder joint you just did. Four-legged buttons are particularly springy. I don't follow my own advice here, but I reckon it's best if the second solder joint is diagonal to the first one. Then you won't need to worry about it moving out of place as you solder the final two. Yeah, I did a messy job on that joint. Too much solder, encouraged by the folded over wire, and because I didn't clamp down the board. In the end, I decided to use my solder sucker to remove the joint and start again, and then tidied up the mess in the crack with a knife. Mostly there, now all I had to do is add the ground and plus 5-volt wires. Moving on to the wiring for the pot. It's nice and simple. 5 volts on one side, ground on the other, and the middle connection outputs to the Arduino analog input. As you adjust the dial on the pot, the Arduino analog to digital converter will measure between 0 and 5 volts. Once again tinning all the contacts. And the controls are now complete.